Welcome to our presentation. Our project is maglev elevator. Today's elevators have some design problems. The most important of these are the need to allocate a large area for the ropes, the elevator shaft, and the area covered by the machine room. Also, the abrasion and deterioration on the contact surfaces. Our system focuses on the solution of these problems. Thanks to the efficient use of the elevator shaft and the ability to work without machine room, our system will increase the usable area by taking up very little space in the used building.
In the 246-meter test tower built by ThyssenKrupp in southern Germany, studies are carried out on magnetic levitation elevators. In this system, the elevator cabin is placed on the slab. Instead of ropes, there are two main rails. The cabin is moved thanks to the magnetic field created by the magnets. In addition, horizontal movement is provided through these slides. Since there are no elements such as ropes which the counterweights are attached, they can go to very high distances that today's systems cannot. Although there have been various academic articles on this technology and studies on control methods, there is no concrete study as much as the studies of ThyssenKrupp company. You can see our technical requirements on the slide. According to our calculations, it will rise to a height of 1.5 meters in 0.96 seconds at maximum acceleration. However, we will not run it with such high acceleration. When it reaches a height of 1.5 meters, speed of the cabin will be 1.92 meters per second. It takes 6.75 seconds to accelerate to 13.5 meters per second and a height of 45.5 meters.
The mass of our magnets is an important factor that directly affects the payload we can carry. For this reason, it's a very important criterion for us to design the smallest sized magnet that can apply the force we want. While two permanent magnets made of 10 by 10 by 2 mm NFA45 material are positioned on the top of the U magnet. Four pieces of 45 by 10 by 30 mm size, 0.5 mm thick, 20 pieces of laminated steel and 80 turns of coil made with copper wire will be used in our system. The mass of each magnet is 167 grams when measured by a precision weighing. While obtaining these dimensions, we paid attention to the lightest state of the system with minimum loss by reducing the size in areas where the effect of the magnetic field is very low. After setting up our coil winding machine in our laboratory for our own system, we used this machine to ensure a smooth coil winding. Each coil consists of 80 turns and its material is 0.8 mm copper wire.
With the help of a component that we design according to our magnet, the magnet will be fixed to the cabinet through the screws on the side of this component. This component was produced with the help of a 3D printer.
For testing the system, we will use a prefabricated skeleton made of sigma profiles, representing the elevator shaft. Here, a weight on which two magnets are fixed will hang with a rope, and metal plates will be placed on both sides of the magnets. Then the control algorithm will be tested on this setup. The air gap will be continuously measured with the sensor fixed to the frame. In order for the assembly to receive a passing rate, the air gap must be fixed on both sides at the desired value in a short time and must react quickly to external disturbing forces. In addition, we will do the calibration process so that our sensor can get correct data during the test. We will fix the sensor at a distance we have measured before and filter it according to the value given by the sensor. In this way, we will minimize measurement errors.
In equation on left, I gives the current, x is distance, n is number of turns, s is area, and u0 is the magnetic permeability of the air. By combining this equation at one point, key A and key B coefficients are obtained. The key A coefficient is the current coefficient and the key B coefficient is the distance coefficient. The linearized equation with these coefficients is seen on the right. The system model of single axis is as follows. After the equation linearity, we can control the system.
Canonical and polynomial form and Manabe method were used to find the PID coefficients. This equation is the polynomial form of our system. We calculated the PID coefficients of our system using the coefficients A's and stability indices in this polynomial form. Gamma stability index and tau time constant is described as seen in the slide. Time constant affects the system response speed as the stability index affects robustness against parameter changes. Coefficients of the characteristic polynomial can be determined as seen on the lower left corner. We can find the general PID coefficients from that polynomial as shown on the lower right corner. We use 2.5 as gamma 1 and 2 for gamma 2 and gamma 3 as Manabe has suggested in his works. This is our PID Simulink model. You can see the PID controller on the left and plant on the right. And this is the output of the PID controller model.
IPD controller was tried with the same coefficient. You can see the output of IPD controller in this slide. You can see the differences between PID and IPD scope outputs. We decided to use the IPD controller as the overshoots disrupts the operation of our system. Here you can see our system's flow diagram. When a reference signal is given to the motor, it is checked that whether the cabinet is stabilized horizontally. If not, magnetic bearing control block runs and controls the system and supplies necessary air gap for operation. When stabilization is provided, the system moves on to motor control. In motor control, necessary current profile is generated, then transformed into ABC currents to be fed to motor drivers.
Electronic part of the system consists of the bearing air gap sensor, electromagnet drivers, motor drivers, and data acquisition card. The sensor used to measure the electromagnet air gap is Omron Z4W. The reaction time of this sensor is 5 milliseconds and has a resolution of 10 microns. We use Simulink Real-Time as the main controller of our system. The interfacing between the electromechanical devices and Simulink is performed with the I/O ports on the Quansar Q8 DAQ card.
OPAP 549 op-amp drivers designed in our lab are used for the control of our magnets. They are designed for easy control of U magnets to be used in maglev-specific applications by our former lab members. We will use the A25A100 PWM as our motor driver, which is a servo drive designed to drive brushless DC motors at a high switching frequency. In this image, you can see the electric panel containing the motor drivers. The panel consists of drivers, contactors, cooling fans, and a 12-volt DC power supply. This panel is readily available in our laboratory. However, a new one will be made in the case of need.
We haven't started production of our motor yet. However, the design and models of the motor have already been prepared. In this diagram, we can see a mathematical model of one of our synchronous Corus linear motors. Calculated inductance and resistance values of our motor is as follows: 228 millihenries and 10.68 ohms. This model is used for controlling motor with voltage signals. In this Simulink file, we use IPD controller to control our model with voltage signal. Control signal goes to our motor model. The model output is Q-axis current. Then this signal is transformed into ABC phases and then sent to the motor. You can see the outputs of the controller.
Some changes were made in the plan we determined in the mechatronic system design stage. As a result of the updating of the academic calendar, the coronavirus, and the changes we made by talking to our professor in our production order, we broke the U-magnet production and testing processes ahead of motor production. We also made minor changes to the deadlines.
We use the Trello application to plan all processes. As in the mechatronic system design process, we also created a plan for the graduation project. We think that when we comply with this plan, we will deliver our project on time. In general, Ali Uğur is responsible for mechanical design and motor design. Bayram Karaca is responsible for electronic and control. Çağan Muhammed Çekeli is responsible for U-magnet design and control. In test processes, all of our members are responsible.
These are our references, and thank you for listening.